Good morning. My name is Graham Spray. I'm the manager of geosciences for AGAT Laboratories. Here at AGAT, we've developed a new educational center, and we're going to be using this to put on some nice technical presentations in the environmental geochemistry, oil and gas chemistry, mining geochemistry, air quality monitoring, and geoscience fields, including rock properties, geology, acid rock drainage, and things of that nature. My own role as manager of geosciences is, of course, on the geology side, and we do a lot of work with oil and gas and, of course, oil sands industry here in Calgary. Today's topic is going to be more in that field. We're going to be talking about the analysis of PostSteam core in a thermal reservoir context, and without further ado, we'll get going. So a PostSteam core is any core that's taken into a steam chamber, and that might be an active steam chamber, a decommissioned or completed steam chamber, or one that's been offline for quite a while. What we're trying to do with any PostSteam core is assess the conditions within the steam chamber. We want to understand how much remaining hydrocarbon there is, what was the effectiveness of the steam production, and we want to compare to any pre-steam core that we might have. What I'll do now is just go through a quick schematic of how a SAGD operation works in principle. We have this fairly simplified block diagram of such a system. And what we have is two wells that are drilled parallel to each other, one above the other, usually about 5 meters apart. The upper of those two wells is used to inject high temperature steam, sometimes mixed with solvent as well. The steam is often at very high temperature, upwards of 200, 220 degrees. And the lower of those two wells is used to drag the bitumen back to the surface. Now, the steam is going to interact with the bitumen in the reservoir as it floods that heat into the reservoir, lower the viscosity of the bitumen, which is naturally very, very viscous, does not want to flow, and that allows it to flow down under gravity to the lower of the two wells. This diagram does simplify things a little bit. For instance, we've got very little overburden visible in this diagram. Usually it's a couple of 100 meters thick, but also the structure in the reservoir is completely simplified. We're just showing the steam chamber idealized shape here. And what we want to do is kind of think a little bit more about how steam flows in reality. So when we look at the architecture of a reservoir, what we actually have is a series of overprinting and self kind of reworking river and fluvial and estuarine systems, certainly in the McMurray Formation. And these have repeatedly over millions of years overprinted themselves and reimagined the meander belt system of that river within a channel context. And so what we have is a series of lateral accretion surfaces within the rock, lateral accretion surfaces creating inclined heterolithic strata, certainly near the top of each channel sequence. That's where we have sand packages interspersed with mud and clay-rich packages. And those mud beds, they can actually extend quite a long way down those lateral accretion surfaces, and they can be reworked by the river, being broken up into rip-up clasts and breccia deposits. These can actually occur at any point, but they are quite common near the base of a channel system. As I said, these channels overprint. You often have multiple stack channels. You can have channels that completely obliterate pre-existing ones, or you can have relict channels that are interspersed with newer ones. You also have changes over time because of changing sea level, which have influenced what depth at which and of course the basin filling, which have influenced what stratigraphic level the channels are active at. On a more broad scale, we also have a ton of complexity. We've got these prairie evaporites which have dissolved deep down, which have created collapse of the overlying carbonates, and this has caused a lot of complexity in terms of the structure and the architecture in the system. Some of this was around the same time as the channel and other depositional events were carrying on, which means that you have a lot of complexity in the depositional environment and the changes in accommodation space that provides. This diagram is really just to show how complex the regional geology is, rather than a specific steam chamber. When we actually get to a specific steam chamber, we need to consider the local structural geology as well as the lithology types that are present. What I'm going to do is walk through one of these cores. This is an example that was cut relatively recently. It is publicly available at the Core Research Center. And in this core, we have a number of different lithotypes, and I want to try and investigate how they interact with the potential flow of steam and oil and the development of the steam chamber within this well. In each of these frames, the core is going from the top at the upper left downward to the right within each of these tubes. These tubes are 75 centimeters long, and then down again into the next tube, and so on. So each one of these frames represents about 3 meters of core. In this particular example, we start off in a breccia zone near the top. That's these dark gray mud clasts that are interspersed and supported in a dark brown sand matrix. That sand is dark brown because it contains residual bitumen. This is bitumen that's not been removed by the SAGD process yet. This well, I believe, had been in production or under steam for about 5 years, so we're not through the life cycle of the reservoir yet. As we continue downward, we get into a zone where you have a much cleaner sand. It starts at the end of that first 75 centimeter tube and continues into the second one. And this sand is really quite clean. It has very little clay present. It also has much less oil. You can see it's a lighter brown shade. And as we continue down through it, it starts to gradually get an increasingly darker brown color, and that's due to increasing residual bitumen. This is a pattern we're going to see repeated in a number of these core images, where we have a sand package that is well swept near the top and becomes less well swept or more bitumen saturated towards the base. And we'll get into that a little bit more because I think it's a very important observation. As we continue down, we get again into some more clast zones, and then we come into a thicker clast here. This may be actually more plate-like, maybe almost in situ, and is quite extensive, possibly. And it has potentially trapped, again, some of this better, more steam-swept sand underneath. So the steam has become trapped up against the underside of this mud bed and then really swept out all the bitumen from here. We have a little anomalous zone here, this lens of bitumen that's sort of residual. Not clear why that's there because there's no mud associated with it to trap it in place. What might have happened is we might have a more microtextural explanation for this. There might be a cementation or some other, a microscopic effect that we would observe potentially with a thin section or SEM to try and understand why that oil became trapped. Continuing downward, though, we're still in really quite well-swept sand. We come through a zone of rubble, and then we continue to the next core. And in the next core, we're actually continuing in the same sand. This is the same sand unit. And from the top there, you can see it's getting much darker brown from where we were in the previous slide. And it gets darker and darker until we hit this very significant mud bed here, this 15 to 20 centimeter thick dark gray mud bed, probably laterally extensive, like a big sheet. And it may be trapping the oil above, because it can't get down through it, and the steam below, because it can't get up through it. So this may be acting as a form of baffle or small barrier within the well. And what we've got then is, again, this similar pattern. We've got very well swept, very clean sand underneath, and poorly swept or a little less well swept bitumen-saturated sand remaining above. Continuing down, we get into a breccia, so that kind of interrupts that normal sequence of a clean sand, but this breccia may have retained a little bit more residual bitumen, and as we continue down through, we're actually going to get through a lot of breccia, and we'll start to see kind of microcosms of that same effect, where you've got a little bit more flat-lying, potentially platy sort of breccia clasts here, and again, we've got a little lens of darker, a little bit more saturated sand above, and lighter, very light tan brown, very well swept sand underneath. That's basically beach sand. It's had all the bitumen stripped out. You can see that in a number of spots through this particular example. And that's a real good example of what's really controlling the way fluids are moving here. You have a low viscosity steam that wants to try and work its way up, and you have a higher viscosity oil that's trying to work its way back down. And they're getting trapped, and they're finding little lenses to get stuck in here and there. As we continue down, I think we may have skipped ahead a little bit for this frame, but we're now into the prime reservoir. This is really clean sand. It's very little clay. Any clay present is just disseminated. We don't have specific clay clasts or mud beds present in this one. And you can see it's very well swept. Most of the darkness here is actually due to not so much residual bitumen as carbonaceous debris, coaly debris fragments that have been carried along and deposited with the sand. That's especially the case in these darker beds in the third tube here. We have these much darker, finely laminated beds. These are actually coaly clasts. Not quite true the same in the second tube here. These darker zones are actually, they do contain residual bitumen, these kind of interfingering, well-swept and less well-swept zones. And what may be explaining that is, again, some kind of microtextural, structural kind of control, something that we would observe with a thin section, perhaps, simply because we can't see any mud beds to explain why that got trapped there. Similarly, in the fourth tube here, we have a little bit of zone of a trapped residual bitumen. Again, that might be explained by a textural effect or a cementation. And now in this, this final frame of the core that I'm interested in, we're into some of really the base of the channel system here. We've got very, very well swept, totally cleaned out sand. It looks dark in places, and that's largely because we have a mix of rock fragments and coal clasts all through it, which create a darker shade to the sand. And then we have a zone of lost core. This metallic look here is actually the aluminum sleeve that the core was captured in. And we've got this core has been lost, likely because it was so well swept that there was no bitumen left gluing it together. Within the McMurray and similar oil sands, the bitumen acts as a kind of glue holding the grains together, and so we can core it. Sometimes when we have a sand that doesn't have the bitumen still there, either we've removed it or it wasn't there to begin with, it just falls apart and you can't really drill it. It's like beach sand. Likely, the producer and injector wells are around here somewhere. We are laterally offset from the longitudinal axis of the steam chamber. So where the injector producer are, we're not directly there, we're somewhere offset, and so we aren't going to see them at the exact same level, but presumably the injector is around here somewhere and the producer may be a bit deeper. So, what did we observe in our little core walkthrough? Well, first thing I want you to take away is that there's a lot of reservoir heterogeneity. We don't just have a great big thick sand package. I mean, it gets that way towards the base, but certainly a lot of the controls on fluid flow and steam chamber development are going to be due to lithological changes. So this creates variable saturation. We saw the effects of some baffles to steam flow or oil flow and some actual barriers, that 20 or 30 or 20 centimeter mud bed there, and it created lenses of steam trapped up underneath and lenses of residual bitumen trapped above some of these features. We also saw the effects of breccias, that they appear to hold on to a bit more residual bitumen, certainly than their sand counterparts. We saw the effects perhaps of some grain size change. I think the breccias may be, in some sense, simply a delaying effect because they don't really impact permeability too much. We've seen that in a number of lab tests. What they do affect, though, is the ability of the steam to heat up that section of the reservoir, simply because the breccias contain a lot of mud and a lot of clay, and that has higher heat capacity than the pure quartz or very quartz-rich sands that we have surrounding them. As a result, it takes longer for the steam to have an effect and actually heat up the bitumen trapped within a breccia. We can consider, of course, that we're laterally offset from the injector and producer pair, so we're not directly aligned, so we're not going to see the base of the steam chamber at the same level that we might expect. And we can also start thinking about what are some of the facies, some of the lithologies, lithotypes that are acting as fluid conduits. They may actually even differ as fluid conduits for steam versus bitumen, so we have to consider that possibility. And of course, if we did have a pre-steam core, we don't for this particular example, but if we did have a nearby pre-steam core, it would be fantastic to just set them out right next to each other and observe directly what some of the differences are. So now we've done our walkthrough, we actually want to try and decide how we're going to go about analyzing this core. What are we going to do with it, and what do we want to get out of it? And one of the first things we're always going to be curious about is the residual saturation. We saw a number of zones where there was residual bitumen still in place, and we want to understand how much is actually there, which then informs how well we're bringing it out of the ground in our production strategy. We also are going to be very interested in the oil characteristics, the chemistry of the oil. Its composition in terms of saturates, aromatics, resins, and asphaltenes is going to be very important. It's a possibility and a hypothesis that the SAGD, and especially enhanced SAGD processes, may be upgrading the oil in situ. That is, leaving some of those asphaltenes behind, which would improve the value of the product. So we'd like to try and determine if that's happening. Assisting with that might be some viscosity work, although in a core like this, it may be difficult to get enough oil to actually do that test. And biomarker analysis, which fortunately requires very little. Trace amounts of oil can be used, and I'll get back to that in a little bit. And then, of course, we want to compare our new data to the pre-steam core or production data as much as we can. Now, as a geologist, my interest is, of course, more on the rock side, and I'm very interested in what we're actually doing to the rock itself, to the sediments, to the minerals that are in place when we subject them to SAGD conditions. We have elevated pressure and temperature, we have chemical changes to fluids that are present, and we have a lot of fluid flow. We have fluid flow in different directions with varying viscosities and rate. We've got that low viscosity steam coming in, and we've got that much higher viscosity. It's lowered, but it's still elevated, of bitumen that's coming back at a lower rate. So what changes can occur? Are we changing the nature of the rock? Are we impacting the potential formation sensitivity and formation damage mechanisms that might play a role in the future? And what are the possible effects on reservoir quality? So I want to get into that a little bit now. And this is going to be a little bit of a refresher for geologists in the crowd. You may remember for first or second year university, this nice type of diagram showing the metamorphic facies chart. Sometimes they're inverted, they're shown the other way with pressure increasing on the y-axis. And for a SAGD project, most of the time we're dealing with pressures and temperatures that are in the zeolite range. So we're getting up here, we're not getting to super high pressure. This is 200 MPa, that's higher than we're getting in these reservoirs, but up in this corner here, maybe even a little higher, is roughly where we're getting to with SAGD conditions. And these conditions can actually have significant impact on the rock. We're going to start having certain phases that are present in the rock are now no longer stable. They're not happy to be at those conditions. They want to go away. They want to change into new phases that are stable and happy at those conditions. So we're going to have some dissolution or reaction of minerals. Certain clays, largely because they have such huge surface area to volume ratio, are going to be very susceptible to these transitions. So we're going to have changes in our potentially removal of kaolinite or illite, or changes to them to different minerals. Smectites as well can be quite susceptible to this. Carbonates are largely going to vanish. We're going to eliminate a lot of our carbonates. Dolomite, calcite, siderite, all going to be dissolved by the high temperature. Feldspars too can be quite severely attacked, plagioclase in particular, and quartz. So this is something that people typically think of as very tough, a very resilient mineral, but a lot of SAGD projects are using injection fluids with elevated pH. And when you have pHs of 10, 11, you're going to get this effect that you can start dissolving quartz. In particular, the parts of the quartz that are susceptible, including quartz grain overgrowths and chert fragments, which are much more susceptible to dissolution. And then you're going to have all these components, these elements that are now dissolved into your pore fluid and the introduced fluid as well. And they can now go on and make new phases that are stable at these pressure and temperature conditions. So some of these new minerals usually include smectite, again, unfortunately. In fact, in some of our projects, we've seen some very complex mixed layer clays developed. Zeolites, I mean, it's called the zeolite facies for a reason. We can actually grow some nice zeolite minerals like clinoptilolite and a couple of other varieties. And we can then have precipitation of quartz and carbonate, depending on the conditions within the reservoir. So you're not going to have uniform temperature conditions through the whole thing. You've got zones where there's going to be a little bit lower temperature, and you might induce precipitation at those locations. You're also going to have an effect where, in particular, the silica would like to drop out at a place where there's a drop in pressure and temperature. And one of the prime places that can happen is at the producer well, unfortunately. And what's going to happen is you can develop a kind of rind, scaled rind around the producer well that then inhibits the permeability of the material directly adjacent to the well, kind of a worst case scenario. So even though the timescales are geologically not even a blink of an eye, we're talking tens of years or 5 or 10 years rather than millions, the conditions that we're putting them under, the high temperature, the high pressure, and especially the elevated pH and fluid flow rates are allowing what are low-grade metamorphic conditions to take place and changes to take place relatively rapidly. So now I want to go through a few nice petrologic examples and some nice images that we have of some of these effects. This is an example from the Clearwater Formation. Clearwater is much more immature sand than the McMurray, so we have a lot of components to play with when we start subjecting them to higher pressures and temperatures. They can also have very complex diagenetic histories themselves. And in this case, we found some really beautiful zeolite grains developed within the pore spaces here, these absolutely pristine, clear little zeolites, very cute. And you can actually tell that they are late because they are crystallized outside the grain rimming clays, which are all around all of these grains. They have a huge amount of grain rimming clay, and you can see that it's actually outside that grain rimming clay. That's very important because it implies that it developed quite late, and it may not be well adhered to the substrate. This is actually from a very similar sample, and it's basically an SEM image showing the exact same thing. The nice tabular mineral right in the middle of this diagram is a zeolite phase. That one is a clinoptilolite, and then surrounding it and upon which it is kind of resting is this beautiful rosette-like bed of grain-rimming clay, which is a corensite mixed layer clay. Corensite is a mixed layer chlorite smectite. So fairly complex, a lot of cation exchange capacity, but also not very well adhered. So if you start having an elevated flow rate, or if you have a chemical change that can cause those clays to start swelling, everything's going to start breaking loose and flowing within the system. We then also have this nice example of plagioclay's grain dissolution. This has an effect that's quite common, but very, very interesting to look at, where the grains have started dissolving along the intersecting cleavage planes. So we have these shards that develop sticking up on the left there, where the frame of the plagioclays used to be. And these shards themselves aren't particularly damaging. They're not really capable of swelling. They might break loose and start flowing with other things. But you have to consider you're releasing a lot of components that used to make up a plagioclase into the fluid that surrounds them. So that would include sodium and calcium and aluminum, silica. These can go on to create those new phases that we're talking about. This example is another good one of some of the problems that we can get if we have kaolinite that's not very well adhered to the substrate, to, in this case, a quartz grain that it's adhered to. You start increasing the flow rate, it can actually start breaking loose some of these grains that are attached. One of the issues with kaolinite in particular is it's a booklet structure. So it's made of these sheets that are stuck together very much like a book. And they can actually start peeling apart themselves. So imagine you take a textbook and you cut off the spine and then you kind of throw it to the wind. These sheets can then start all flying up and going along with the fluid flow that surrounds them, and then start plastering up against each other and really choking out permeability. This is an example of an Alight clay. Typically, you don't see it with this type of structure in the Manville group, but it is a really good example of some of the forms that Alight can take. This is a very hair-like kind of structure. And what it kind of illustrates, again, is if this starts to deflocculate, if this starts to break loose, we are going to get an effect that it can move through and then very easily plug up within your permeability system, within the pore throats. We found this very interesting effect that isn't particularly common, but can have a huge impact, and that's a cation exchange induced clay deflocculation. And that's where you have a clay that naturally has a divalent cation in its interlayer space, for instance, calcium, which is 2+. And then you introduce a fluid that is monovalent, like a monovalent brine. So for instance, KCl or NaCl. And the interesting thing was we observed this with KCl, which is typically considered very benign for oil and gas production and completion and testing purposes. And what happens is, we've learned, and it was very surprising to us at first, the potassium can replace the calcium, can replace that divalent cation in the interlayer space. And with the monovalent cations in there now, they're not holding on as tightly. They're not gripping together as effectively. And so the sheets can begin to peel off and deflocculate. And you get that same effect I was talking about with the kaolinite, where it's like if you've cut off the spine of a book and then throw the sheets. So again, the chemistry as well as the fluid flow can have an impact on these clays and on the other minerals that are present. And really, I guess the point is, introduce new methods of formation or new types of formation sensitivity that necessarily weren't there before. In order to assess some of the effects, what we typically do is we will analyze a pre-steam core as well as we can. We'll use a number of techniques, potentially including XRD, thin sections, scanning electron microscopy, QuemScan, XRF, just regular core analysis. And then we will build a kind of a list of the formation sensitivities that we think that this reservoir may be susceptible to. We'll then go ahead and use that information to inform how to do some special core analysis. We'll take plugs of that core and we'll then do core testing, where we soak and flood the fluids that we're planning to use in the reservoir into those core plugs and actually see what happens. We can then take those and we can rip those apart and analyze them and figure out what may have gone wrong, what may go wrong in the field, and how might we mitigate that. We then also will be able to carry out post-steam core analysis. So if we have that core that comes in later on, we want to compare to that upfront work and really try and assess how we're doing. I mentioned biomarkers a bit earlier. It's really an area that we've seen a lot of use in recently. We've taken off quite a lot more. There's certainly been a a lot of interest in biomarkers in the heavy oil world, and for good reason. They do allow a very sensitive comparison of the composition of different oils. So you can look at the degree of biodegradation, you can look at a very wide range of compounds, compound ratios, and this allows you to really fingerprint a particular oil very precisely. And so what we can do is we can use this in pre-steam planning. So before we even start to apply steam to a reservoir, in our pre-steam cores, we can analyze a number of points through the reservoir to try and assess how the biomarker ratios vary. If you have a large step in biomarker variation, it might imply that there's not very good fluid communication between two parts of a reservoir. So this would give you some upfront indications of reservoir compartmentalization. They can also, in some cases, assist with understanding where oil is coming from during production. So we can compare our pre-steam core analysis of biomarkers to produced oil and actually understand which parts of the reservoir were the most effective, which ones are we pulling the most oil out of here. And of course, when we come to post-steam core, there's a whole range of things we can try and do with biomarkers. We want to try and understand which are the productive reservoir zones. So we can look again at compare versus produced oil and compare to the pre-steam oil as well. We can also potentially try and find oil migration evidence. So we can maybe look for oil that has a fingerprint that in the pre-steam core was much higher elevation within the well. And we might be able to actually observe some of the drainage. We may also be able to look for the depletion of certain compounds or classes preferentially. This relates to what I was talking about with the SARA analysis, where the hope is that we might actually be upgrading some of this oil in situ. The biomarkers may be able to give us some clues in that regard. So just to sum up, a post-steam core analysis study is really to help us understand system performance. We want to consider and interpret the chamber development, and we want to observe the steam and oil migration pathways and try to theorize about how those pathways develop and how they might behave over time through a reservoir. We want to try and investigate reservoir compartmentalization compared to any of our predictions about it, whether we actually see what we thought might happen. And then we want to select sample locations. We want to actually try to assess what we're seeing still remaining in the core in that particular steam chamber, looking at saturation, looking at oil quality, and then looking also at those mineral and textural changes to look for things that might present a problem down the road. There's a lot of initiative now to try and move into, with some of these aging reservoirs, can we use the former steam chambers for a new purpose? For instance, wastewater disposal. That may have a completely different implication for the formation sensitivity, and so we need to look at these mineral and textural changes that have been induced by the steam conditions, because that may give it a whole new context for injecting new fluids for disposal. And of course, when it comes to actually considering the production of the well, we want to tie everything back to the lab data and the field data as well. So we want to tie back to our observation wells, microseismic, anything else we have that might give us some clues here. So thank you very much. I really enjoy chatting about these sorts of topics. The questions of mineral changes and phase changes induced by steam conditions is really quite fascinating to us here. And what we would like to do is really try to carry out more of these types of technical talks over the next few months. As I mentioned, we have a number of research initiatives in different fields: environmental, mining geochemistry, oil and gas chemistry, and others. And we're really going to try and take advantage of this educational opportunity to use this nice facility we've constructed here. So with that, thank you once again, and have a great day.